The vacuum of space is not what it seems. It holds the universe's ultimate blueprint. We are about to journey into the hidden architecture of nothingness. The physicist John Wheeler once said that space-time tells matter how to move, and matter tells space-time how to curve. This conversation between something and nothing is the heart of a cosmic mystery. By the end of this exploration, your understanding of reality itself will be fundamentally reshaped. We will uncover how this apparent emptiness dictates the fate of galaxies and sparks particles into existence. We will see why the vacuum is the most important something in the cosmos. How do you think nothing can be the foundation for everything? That profound conversation between matter and space-time happens within a medium we often misunderstand. We picture the vacuum of space as a perfect, sterile emptiness, a true void where nothing exists. But science reveals a far more fascinating truth. A cosmic vacuum is not nothing. It is the lowest possible energy state a field can possess. Think of it like a calm ocean stretching to the horizon. From a distance, its surface appears perfectly flat and motionless. Yet up close, you would see it is alive with tiny, ceaseless ripples and subtle currents. The vacuum is like that serene ocean. It is not empty. It is a state of profound potential, the foundational baseline of reality. Underpinning everything are quantum fields. These are not physical things you can touch. They are more like fundamental properties woven into the fabric of space-time itself. An electron field, a quark field, a Higgs field, they exist everywhere at all times. Even in the deepest, darkest void between galaxies, these fields are present. When we say a region of space is empty, we merely mean that these fields are in their quietest, most relaxed state. They are not excited enough to manifest what we recognize as a particle. But they are still there, thrumming with latent energy and possibility. This redefinition is a seismic shift in perspective. The vacuum is not a passive stage upon which the cosmic drama unfolds. It is an active, dynamic participant, the very substrate from which all particles, forces, and phenomena emerge. Recognizing this turns our common sense on its head. The true foundation of the universe is not solid matter, but this vibrant, energetic nothingness. And if this baseline state holds such power, what happens when it is disturbed? The idea that nothingness could be a foundational reality is a debate stretching back millennia. Long before quantum fields, the ancient Greek philosopher Democritus and his teacher Leucippus proposed a radical theory. They suggested that everything in the cosmos was made of tiny, indivisible particles they called atoms. But for these atoms to move, to combine and form the world we see, they argued there had to be an empty space for them to move through. They called this the void, a true nothingness that was as real and necessary as the atoms themselves. This was a breathtaking leap of intuition, the first scientific proposition that emptiness had a structure and a purpose. Yet this view was not universally accepted. The towering intellectual figure of Aristotle vehemently disagreed. He argued that nature abhors a vacuum, that empty space was a logical impossibility. For Aristotle, the cosmos was a plenum, a realm completely full of substance, with no room for true nothingness. His authority was so immense that this belief, that a vacuum could not exist, held sway over Western science for nearly 2,000 years. The intellectual dam finally broke during the scientific revolution. In the 17th century, the Italian physicist Evangelista Torricelli filled a long glass tube with mercury and inverted it into a dish. The column of mercury dropped, but only partway, leaving an apparently empty space at the sealed top. Torricelli had created the first sustained artificial vacuum. He correctly deduced that it was not some mysterious force holding the mercury up, but the sheer weight of the air itself pushing down on the dish. Nothing was, in fact, pushing back. Soon after, the German mayor and inventor Otto von Guericke conducted a stunning public demonstration. He crafted two large copper hemispheres, mated them together, and used a pump he invented to suck the air out from inside. He then harnessed a team of horses to each hemisphere and showed that not even 16 horses, straining in opposite directions, could pull the hemispheres apart. The power of the vacuum of nothing was holding them together with immense force. These experiments were a profound shock to the scientific world. They proved that nothing was not just an abstract concept, it was a physical reality with measurable, powerful effects. The philosophical ground had shifted. The question was no longer if a vacuum existed, but what its true nature was. For centuries, scientists believed they had finally found true emptiness, a sterile void. They had no idea they were merely peeling back the first layer, and that an even deeper, more vibrant nothingness was waiting to be discovered. The stage was now set for a revolution that would come from an entirely new realm of physics. The classical vacuum, a placid emptiness held shut by the force of air, was about to be shattered. The quantum revolution of the early 20th century did not just add new particles to the universe, it rewrote the very definition of nothing. At the heart of this upheaval was a deceptively simple idea from Werner Heisenberg. His uncertainty principle stated a fundamental limit to what we can know. You cannot simultaneously pinpoint both the exact position and the exact energy of a particle with perfect accuracy. The more you know about one, the less you can know about the other. This is not a limitation of our machines, but a fundamental rule woven into the fabric of reality itself. Apply this rule to the void, and the concept of a perfect vacuum collapses. For a region of space to be truly, perfectly empty, it would need to have exactly zero energy forever, but the uncertainty principle forbids such perfect stillness. The energy of a point in space cannot be precisely pinned to zero, even for an instant. It must fluctuate. This is the birth of the quantum fluctuation, a brief, spontaneous shudder in the underlying fields. These fluctuations are so profound that they can momentarily conjure particles into being. A particle and its antimatter partner can pop out of the nothingness, exist for a fleeting moment, and then annihilate each other, returning their borrowed energy to the vacuum. We call these virtual particles, and their frenetic activity turns the old, sterile void into a bubbling cauldron of potentiality. Imagine the calm ocean we pictured before, but now we see it is simmering, with countless tiny bubbles of existence constantly forming and popping across its entire surface. This is the true quantum vacuum, a seething, energetic foundation that is never truly at rest. This ceaseless activity is not just a theoretical curiosity, it has a force, a palpable push against the fabric of the cosmos. These quantum fluctuations are not just a mathematical abstraction. Their existence produces a physical force we can actually measure in a laboratory. In the late 1940s, the Dutch physicist Hendrik Casimir performed a brilliant thought experiment that would later bear his name. He imagined placing two perfectly smooth, uncharged metal plates into a perfect vacuum, positioning them so close together they are almost touching. In the classical, empty view of the vacuum, nothing should happen. The plates should remain motionless in the void. But Casimir, thinking in terms of the new quantum reality, predicted they would be drawn together by an invisible hand. The reason lies in the sea of virtual particles. Think of the vacuum as a turbulent ocean of waves, with every possible wavelength present. When the two plates are brought extremely close, only certain wavelengths of virtual particles can fit in the narrow gap between them. It is like a guitar string that can only vibrate at specific frequencies. Longer wavelengths simply cannot exist in that confined space. Outside the plates, however, every wavelength is possible. This creates a pressure imbalance. The relentless activity of virtual particles outside the plates pushes inward with more force than the more limited set of particles pushing from within the gap. The net result is a tiny but measurable force that squeezes the plates together. For decades, this was a stunning prediction. Then, technology caught up. Scientists have since performed this experiment with incredible precision, using modern tools to position the plates mere nanometers apart. The result, the plates do indeed move, pulled together exactly as Casimir foretold. This is not a theory anymore, it is a confirmed, observable fact. The Casimir effect is a direct witness to the seething quantum activity of empty space. It proves that the vacuum is not passive. It is a dynamic medium that exerts real pressure on the objects within it. If the vacuum can push on plates, what other, grander influence might it have on the cosmos itself? The Casimir effect reveals a vacuum alive with motion. But to grasp its true nature, we must look at the universe's underlying canvas. Quantum field theory provides this revolutionary perspective. It proposes that what we call reality is not built from tiny, solid balls of matter, but from something far more fundamental: fields. These are not physical things like a magnetic field you can feel. Instead, think of them as invisible properties, a set of rules and potentials that are woven into the very fabric of spacetime. An electron field exists everywhere. A quark field permeates all of space. The Higgs field is a constant presence throughout the cosmos. Even in the deepest, most perfect vacuum, these fields are there. They are not excited, but they are present. So what then is a particle like an electron? It is not a solitary speck. An electron is simply a localized excitation, a tiny knot of energy or a vibration in the universal electron field. It is a brief, intense concentration of the field's energy that we have learned to recognize and label. A helpful analogy is a mattress. You do not see the individual springs and the stuffing when you look at a mattress. You see a smooth, continuous surface, but the entire behavior of the mattress, how it supports you, how a ball bounces on it, is determined by the hidden arrangement of those springs. Now drop a heavy ball onto that mattress. It creates a pronounced dimple, a localized disturbance that moves energy through the springs. That dimple is like a particle, a specific excitation traveling through the underlying field. The vacuum, in this view, is simply the mattress in its default, undisturbed state. It is the lowest possible energy configuration of all these cosmic fields. This field-centric view is not just a philosophical shift, it is essential for modern physics. It is how we understand the origin of mass itself. The Higgs field, for instance, is like a kind of cosmic molasses that fills this vacuum. As certain particles move through it, they interact with this field, and that interaction is what we experience as their mass. Without this vibrant, field-filled vacuum, the universe would be a ghostly, weightless realm, utterly unrecognizable and unable to form the stable structures we see today. This foundational activity raises a monumental question. If the vacuum is this dynamic, what happens when its energy is not zero, but something far greater? This omnipresent field is the very reason anything has substance at all. The Higgs field is arguably the most famous resident of the quantum vacuum, and its sole purpose is to give mass to the universe. But it does not act like a drag, as it is often described. Instead, think of a world-famous celebrity trying to walk quickly through a packed, adoring crowd. They are not being pulled backward by some external force. Their progress is slowed because they are constantly interacting with the people surrounding them, shaking hands, exchanging brief words, navigating the throng. This continual interaction is what gives them a kind of social inertia, making it difficult for them to change their speed or direction quickly. In the cosmos, the Higgs field is that crowd filling all of space. Fundamental particles are the celebrities. A particle that interacts strongly with this field, like a top quark, finds its path hindered. It takes more energy to get it moving and to change its motion. This resistance to acceleration is what we perceive and measure as mass. A particle like a photon, which does not interact with the Higgs field at all, feels no crowd. It zips through the vacuum at the ultimate speed limit, the speed of light, completely massless. This mechanism transforms our understanding of the vacuum. It is not an inert stage. It is an active participant that endows the actors with their most fundamental properties. The discovery that confirmed this breathtaking idea was one of the most significant in modern science. For decades, the Higgs field was a brilliant but unproven prediction. Then, the immense particle collider at CERN went to work, smashing protons together at energies that recreated the conditions of the early universe. From the debris of these collisions, scientists at the Large Hadron Collider identified a telltale signature, a fleeting ripple in the Higgs field itself. They called it the Higgs boson. This particle was not the field, but a crucial excitation of it, like a splash in the cosmic molasses that proved the molasses was really there. Its discovery in 2012 was a monumental triumph. It confirmed that the vacuum, this apparent nothingness, is directly responsible for the substance of our world. The solidity of your desk, the weight of your own body, all of it is a gift from the vibrant, energetic void. If the vacuum can create mass, what other, more dramatic creations might it be capable of? This vibrant vacuum, the source of mass and motion, holds a secret so immense it threatens to unravel our understanding of physics. The endless dance of virtual particles, confirmed by the Casimir effect, should imbue every single cubic centimeter of empty space with a staggering amount of energy. We call this vacuum energy, and quantum field theory calculates its strength. The number it gives is so colossal, it is almost impossible to grasp. It suggests that the energy contained in the space inside a single coffee mug should be enough to boil every ocean on Earth instantly. This is the raw, latent power predicted to be woven into the fabric of nothingness itself. Decades before physicists even conceived of quantum fluctuations, Albert Einstein encountered a related puzzle. When he crafted his equations of general relativity, which describe how matter and energy warp space-time, he found they predicted a universe that was either expanding or contracting. Believing the cosmos to be static and eternal, he introduced a fudge factor, a term he called the cosmological constant. Its purpose was to represent a repulsive energy inherent to empty space, a kind of anti-gravity that would precisely balance the inward pull of matter and keep the universe still. He later called this his greatest blunder, but the story was far from over. We now know the universe is not static, it is expanding. And yet, the cosmological constant was resurrected with a new purpose, to represent the vacuum energy driving that expansion. This is where we encounter the most embarrassing problem in all of theoretical physics. When we compare the theoretical prediction for vacuum energy with the actual, observed value from measuring the universe's expansion, the numbers do not just disagree, they are catastrophically wrong. The calculated value is about 120 orders of magnitude larger than what we see. To understand that level of error, imagine predicting the distance from Earth to the entire observable universe. but your calculation instead gives you a size smaller than a single proton. The discrepancy is that profound. This is the cosmological constant problem, a screaming void in our knowledge, indicating that something fundamental is missing from our picture of reality. Somehow, the universe is fine-tuned to an almost impossible degree, cancelling out nearly all of this vacuum energy, leaving behind only the faintest whisper that nevertheless shapes the fate of everything. This staggering miscalculation of vacuum energy forces us to confront the universe's most dramatic behavior. In the late 1990s, two independent teams of astronomers were observing distant stellar explosions known as Type I, a supernova. They were trying to measure how much the universe's expansion was slowing down over time, expecting to see the collective gravity of all matter putting a brake on the cosmic flight of galaxies. What they found, to their profound shock, was the exact opposite. The expansion of the universe is not slowing down at all. It is accelerating. Galaxies are flying away from each other at a faster and faster rate, as if some mysterious, repulsive force is stretching the very fabric of spacetime. This discovery, which earned a Nobel Prize, required a name for the unknown culprit, dark energy, and the most compelling candidate for this cosmic push is the energy of the vacuum itself. Think of the vacuum not as an empty stage, but as a springy, self-replenishing foam. Every cubic centimeter of this cosmic substrate possesses a tiny, intrinsic energy. According to Einstein's equations, this energy creates a negative pressure, a kind of cosmic tension, while normal positive pressure, like in a balloon, pushes inward and pulls things together. Negative pressure does the opposite. It acts as a repulsive force, causing space itself to stretch. The vacuum is not pulling or pushing on galaxies from the outside. Instead, as more vacuum comes into existence, its inherent negative pressure drives an exponential self-stretching of the cosmos. The void is actively generating the space that pushes galaxies apart. This realization elevates the vacuum from a backdrop to the lead director of cosmic evolution. The fate of the universe, whether it will expand forever into a cold, dark emptiness or eventually recollapse, is dictated by the properties of this apparent nothingness. The hidden architecture of the vacuum, with its seething quantum activity, is writing the final chapter of everything. But if this energy is so powerful, why is its effect so subtle and fine-tuned, allowing galaxies and life to form at all? This primordial vacuum energy did not just shape our present, it forged the entire cosmos in its first fleeting moments. The theory of cosmic inflation reveals a vacuum so potent it acted as the universe's own creation engine. Picture the newborn universe, less than a trillionth of a second old. According to this idea, it was filled with a vacuum in a peculiar condition. This was not the quiet, low-energy vacuum of today, but a false vacuum, a state of tremendously high energy, like a ball carefully balanced on the very peak of a steep hill. It was a state of unstable perfection, pregnant with potential. Then something triggered the transition. The metaphorical ball began to roll down the hill. As it descended toward the true, low-energy vacuum at the bottom, the universe underwent a transformation so violent it defies all intuition. The energy locked within that false vacuum state was released, not as heat or light, but as a repulsive force that caused space itself to expand at an exponential, faster-than-light rate. In a span of time almost too brief to comprehend, a region smaller than a subatomic particle was stretched to a size larger than our entire observable universe. This was not an explosion of matter into space, but a hyper-stretching of the fabric of spacetime. This single, vacuum-driven event elegantly solves puzzles that plagued cosmology for decades. Why does the universe appear so uniform in every direction we look? Because inflation stretched a tiny, homogeneous patch to encompass everything we can see. Why is the geometry of the universe so remarkably flat? Because inflation stretched the fabric of space so dramatically that any initial curvature was smoothed away, like blowing up a tiny, wrinkled balloon to the size of the Earth. Most profoundly, the quantum fluctuations simmering in that primordial vacuum were not left behind. They were stretched too, imprinted across the cosmos as tiny variations in density. These microscopic ripples in the fabric of nothingness became the gravitational seeds for everything that followed. They were the blueprint for galaxies, galaxy clusters, and the vast cosmic web we see etched across the sky today. Every star, every planet, every structure we call home owes its ultimate origin to the subtle tremors within that primordial nothingness. The vacuum provided the script, and inflation amplified it to a cosmic scale. These ghostly entities are the universe's ultimate ephemeral actors. We call them virtual particles, yet that name is almost a misdirection. They are not tiny, solid balls that pop into existence from some hidden reserve of matter. They are better understood as fleeting wrinkles or spontaneous knots of energy in the underlying quantum fields. Their entire existence is a delicate dance with one of reality's strictest bankers, the uncertainty principle. This fundamental law allows them to borrow energy from the vacuum, but there is a critical condition. The loan must be repaid, and the more energy they borrow, the faster they must pay it back. A significant energy debt might allow a pair of particles to exist for a minuscule fraction of a second, while a tiny loan could permit a slightly longer, but still immeasurably brief, life. This constant, frantic borrowing and repaying is what gives the quantum vacuum its simmering, energetic character. You might wonder how something so temporary could possibly matter. Their influence, however, is written into the very light we see and the stability of the atoms that build our world. Consider the hydrogen atom, the most simple and abundant element. In a classical world, its single electron should orbit its proton at one very specific, predictable energy level. But when physicists measured it with extreme precision, they found a tiny, unexpected shift in that energy. This is the Lamb shift, and it is caused by the electron constantly interacting with the swarm of virtual particles flickering around it. The electron's path is subtly altered by this ghostly crowd, a measurable effect caused by entities that are never directly seen. An even more dramatic role for these virtual particles emerges at the edge of a black hole. Space-time is so warped there that the gravitational pull is irresistible. According to the theory of Hawking radiation, a virtual particle pair can pop into existence right at the event horizon, the point of no return. Under normal circumstances, they would annihilate each other instantly. But here, the immense gravity can tear them apart. One particle falls into the black hole, while the other escapes into space, becoming real. The energy for this transformation is effectively stolen from the black hole's gravitational field, causing the black hole to slowly, over eons, evaporate. Virtual particles, these transient ghosts, are therefore responsible for the eventual demise of the universe's most destructive objects. They are not merely mathematical quirks. They are essential cogs in the machinery of physical law, their brief lives leaving permanent imprints on everything from the atom to the cosmos. If such profound effects spring from these fleeting disturbances, what does that suggest about the true substance of the fields they ripple? These virtual particles ripple across a stage we assume is perfectly smooth, but even space-time itself has a hidden, granular texture. When we push our understanding of reality down to the very smallest conceivable scale, a place known as the Planck length, the serene continuum of Einstein's universe dissolves into a state of ultimate chaos. This is the domain of quantum foam, The Planck length is almost impossibly tiny, about a trillionth of a trillionth the size of a single proton. At this scale, the uncertainty principle wages a war on geometry itself. It becomes impossible to precisely measure the fabric of spacetime, because doing so would require concentrating so much energy into such a minuscule volume that a tiny black hole would spontaneously form. The result is a fundamental blurring of reality's foundation. Spacetime is no longer a smooth, woven fabric. It becomes a bubbling, frothing sea of probabilistic foam. Imagine viewing the ocean from a high-flying aircraft. Its surface appears as a vast, unbroken sheet of glass, a perfect continuum, now dropped down to the molecular level. That serene surface vanishes, replaced by a frenetic storm of individual water molecules, a chaotic spray where the very idea of a continuous surface breaks down. The quantum foam is the cosmic equivalent of that molecular chaos. In this foaming spacetime, the topology of the universe is in constant, violent flux. Tiny wormholes may flicker in and out of existence. The geometry of space might momentarily resemble a multiply-connected foam bubble, only to reconfigure itself an instant later. This turbulent activity represents the ultimate graininess of the cosmic blueprint, a fundamental pixelation of reality. Here, our everyday logic completely fails. The clean, deterministic flow from cause to effect, the very meaning of before and after, may become meaningless concepts in this primordial frenzy. This bizarre prediction arises from the desperate need to unite the two pillars of modern physics, quantum mechanics and general relativity. One governs the probabilistic, fuzzy world of the very small. The other describes the smooth, geometric curvature of the cosmos. They are both spectacularly successful in their own domains, but they speak different languages and become mathematically incompatible at the scale of the quantum foam. Uniting them into a single theory of quantum gravity is perhaps the greatest unsolved problem in physics. The existence of this foaming structure is a direct challenge to our most basic assumptions. We perceive a universe of definite locations and a clear flowing river of time, but its foundation appears to be a probabilistic storm where space and time themselves lose their identity. If the very threads of the cosmic tapestry are this wild and uncertain, what does that say about the nature of the reality we experience? This quantum foam suggests a chaotic foundation, yet some physicists see a strange kind of order emerging from it. They propose a breathtaking possibility that the vacuum of space itself could be a cosmic superfluid. A superfluid is an exotic state of matter with a property that seems to defy common sense. It flows with absolutely zero viscosity or friction. On Earth, we can create superfluids by cooling certain liquids like helium to temperatures near absolute zero. In this state, the liquid can climb up the walls of its container and flow through impossibly tiny cracks without any loss of energy. Now imagine if the entire fabric of spacetime, the vacuum itself, shared this property. This is not just a poetic metaphor, but a serious theoretical model that could elegantly solve some of physics' deepest puzzles. If the vacuum is a superfluid, it would provide a continuous, frictionless medium that perfectly explains why the universe allows for such smooth, persistent motion over cosmic distances. Planets glide in their orbits for billions of years without slowing down, not because space is an empty void, but because it is an ultra-slick fluid offering no resistance. This perspective completely reimagines the nature of reality. In this superfluid vacuum theory, what we perceive as fundamental particles might not be tiny dots at all. They could be like dynamic vortices or whirlpools within this flowing cosmic medium. Just as a vortex in water is a stable, recognizable structure made entirely of water itself, An electron could be a specific, self-sustaining twist in the superfluid fabric of spacetime. Its properties, like mass and spin, would be determined by the precise nature of that twist. This idea offers a radical new way to understand gravity. Einstein's general relativity describes gravity as the curvature of spacetime. A superfluid vacuum provides a physical medium that can actually curve and flow. The presence of matter, like a star, would then create a kind of drain or vortex in the superfluid, and the flow of the fluid itself would guide other objects like planets along curved paths. We perceive this flow as the force of gravity. This framework elegantly bridges the microscopic and the cosmic, suggesting that the laws governing the universe's largest structures emerge from the collective behavior of its most fundamental fluid-like substance. Reimagining the cosmos as an ultra-exotic fluid opens up profound questions about the very nature of motion and form, reshaping our understanding of the force that molds the universe. This cosmic superfluid, if it exists, would have a shape dictated by the very things moving within it. This brings us to the true nature of gravity, the force that sculpts the universe. Einstein's great insight was that gravity is not a mysterious force pulling across empty space. It is the geometry of nothingness itself. Mass and energy do not emit a gravitational field. They warp the very fabric of spacetime. The vacuum is not a passive stage. It is a dynamic, malleable substance that curves, stretches, and compresses. Think of a vast, taut rubber sheet representing the undisturbed vacuum. Now place a heavy iron ball in its center. The ball creates a deep, smooth depression in the sheet. If you then roll a smaller marble nearby, it does not travel in a straight line. It follows the curve created by the heavy ball, spiraling inward as if pulled by an invisible hand. The marble is not being pulled. It is simply following the simplest path through the warped landscape. This is the essence of gravity. The planets orbiting our sun are not being tugged by some cosmic string. They are following the invisible contours, the grooves and curves that the sun's immense mass imprints upon the quantum vacuum. What is truly being warped is the architecture of empty space, the foundational field-filled medium we have been exploring. The heavy ball warps the rubber sheet's two-dimensional geometry, and in our three-dimensional universe, mass warps the four-dimensional geometry of spacetime. This curvature is what guides the motion of everything from a falling apple to the majestic dance of galaxies. The blueprint of reality is not a static, rigid plan. It is a living document, constantly being rewritten by the matter and energy it contains. The vacuum's geometry responds to the presence of a star, and that new, curved geometry then instructs the star and everything else how to move. It is a continuous, elegant conversation between something and nothing, where the shape of the void gives the universe its structure and form. This warping of nothingness reaches its logical extreme with a startling prediction. An astronaut floating in the dark, perfect vacuum of deep space would feel only the cold embrace of absolute zero. They would detect nothing, no particles, just the quietest possible state of the universe. But if that same astronaut were to fire their rockets and accelerate continuously, their experience would transform dramatically. From their new, accelerating perspective, the void would no longer be empty. They would find themselves immersed in a warm bath of radiation, a glow of real particles where before there was only nothing. This is the Unruh effect, and it reveals that the vacuum itself is a matter of perspective. What one observer calls emptiness, another calls a populated universe. This is not an illusion or a measurement error. From the accelerating astronaut's point of view, the radiation is utterly real. It has temperature and energy, and it would feel just as tangible as the warmth from a fire. The key lies in the very nature of acceleration, which creates a type of horizon, much like the event horizon of a black hole. Virtual particles that were forever hidden from the coasting astronaut can now be detected by the one pushing forward, their energy loan made permanent by the constant motion. This shatters the idea of an absolute, objective vacuum. The particle content of the universe is not a fixed inventory. It depends entirely on your path through space-time, on your own state of motion. This blurs the line between something and nothing in a way that is both beautiful and deeply unsettling. Is a particle truly there if it only exists for one observer and not for another? The Unruh effect forces us to admit that existence itself is a relative concept, woven from the relationship between the observer and the vibrant, field-filled void. This strange phenomenon creates a profound bridge between the three great pillars of physics. It ties the quantum nature of particles to the relativistic nature of motion, and it even introduces thermodynamics into the mix, because the perceived radiation has a precise temperature. This is not just three theories coexisting. It is a glimpse of a deeper unity, a single, interconnected tapestry where motion through nothing can conjure something from the sheer act of acceleration. This staggering miscalculation is known as the vacuum catastrophe, and it represents the single greatest failure of a scientific prediction in human history. The number 1 with 120 zeros after it is not just a big number. It is a measure of our profound ignorance. If the theoretical calculation for the energy of the vacuum were correct, the repulsive force of this energy would have ripped the universe apart in its first instant, preventing any galaxy, star, or planet from ever forming. The fact that we exist to even ponder this problem means the actual value of vacuum energy is almost exactly zero, but not perfectly zero. It is fine-tuned to a degree that is utterly baffling. To say this is a discrepancy is like saying the Pacific Ocean is a little bit damp. The vacuum energy we predict should be a cosmic tsunami, yet we observe only the faintest, most gentle ripple, just enough to explain the accelerating expansion. Physicists have proposed several escape routes from this embarrassing puzzle. One leading idea is supersymmetry, an elegant theory that posits every known particle has a hidden superpartner. In this symmetrical world, the positive and negative contributions of virtual particles and their superpartners would perfectly cancel out, driving the net vacuum energy to zero. It is a beautiful solution, but there is a catch. We have never found a single one of these superpartner particles, despite searching for them in our most powerful colliders. If supersymmetry exists, it is a broken symmetry, and its perfect cancellation is lost, leaving us back at the catastrophe. Another, more philosophical proposal is the Anthropic Principle. This suggests that our universe is just one of a vast, perhaps infinite, multiverse. In each of these universes, the fundamental constants, including the value of the vacuum energy, are set randomly. We, of course, find ourselves in one of the exceedingly rare universes where the value is minuscule enough to allow for galaxies and life to evolve. We are not here because the number is special. We are here because only in a universe with this specific number could we exist to observe it. For many scientists, this feels less like an explanation and more like a surrender, a way of saying the fundamental laws are ultimately arbitrary. These proposed solutions highlight a deep and unsettling truth. The vacuum catastrophe is not a small crack in our model of the cosmos. It is a chasm, a screaming void in our understanding that tells us our most cherished theories are fundamentally incomplete. The blueprint we have been deciphering, for all its elegance and predictive power, is missing entire chapters. The very fabric of reality holds a secret that our current mathematics cannot yet describe. A century ago, physicists believed they had permanently banished a ghost from the machine. The luminiferous ether was a hypothetical substance, an invisible medium that was thought to fill all of space, serving as the necessary carrier for light waves, much like air carries sound. But a series of brilliant experiments, most famously by Michelson and Morley, failed to detect any sign of this stationary ether. There was no cosmic wind to be felt as Earth moved through it. This failure was a profound puzzle until a young patent clerk named Albert Einstein proposed a radical solution. What if the ether simply did not exist? His theory of special relativity did away with it entirely, showing that light did not need a medium and that the laws of physics were the same for all observers moving at constant velocity. The ether was declared a scientific relic, a beautiful idea killed by a stubborn fact. Yet today, as we describe a quantum vacuum brimming with energy, seething with virtual particles, and warping under the influence of mass, a startling question emerges. Have we inadvertently brought the ether back to life in a far more sophisticated and bizarre form? The parallels are undeniably intriguing. Both concepts describe a ubiquitous, non-material something that fills the emptiness of space. Both are meant to serve as a substrate for physical phenomena, whether for light waves in the 19th century or for quantum fluctuations and the Higgs field in our own. The old ether had mechanical properties, imagined as a kind of rigid jelly. The new vacuum has measurable properties too, like a negative pressure and an energy density. So, is the quantum vacuum just the old ether wearing a modern disguise? The crucial difference lies in a single, powerful property, Lorentz invariance. The old ether was a fixed stage, an absolute frame of reference against which all motion could be measured. It provided a universal rest frame, which is precisely why its failure to be detected was so devastating. The quantum vacuum, however, is no stage. It offers no preferred state of rest. An observer moving at constant speed through the vacuum measures the exact same laws of physics as an observer at rest. The vacuum itself has no wind, no directionality you can point to. It is a democratic medium treating all inertial observers equally. This is not a stationary substance, but a dynamic and responsive feature of spacetime itself. This historical reflection is more than a curious footnote. It shows how a discredited idea can be reborn, not in its original form, but in a more complex and physically consistent incarnation. The ether did not return, but the problem it tried to solve, the nature of the space between things, never truly went away. It simply demanded a deeper, less intuitive answer. This evolution of thought humbles us. It suggests that our current, wildly successful models of the quantum vacuum and spacetime may themselves be transitional. They explain so much, yet they contain a catastrophic failure in the vacuum energy calculation. They may be the stepping stones to a future theory, one that will make our current understanding of nothingness look as quaint and incomplete as the luminous ether appears to us today. This relentless expansion driven by the vacuum does more than just push galaxies apart. It may also be the engine that drives time itself forward. We all experience the arrow of time, the undeniable flow from a definite past into an uncertain future. We remember yesterday but not tomorrow. A shattered cup never spontaneously reassembles itself. This one-way direction is described by the second law of thermodynamics, which states that the total disorder or entropy of a closed system always increases. But why did the universe start with such incredibly low entropy in the first place, creating a slope for time to slide down? The answer may be written into the architecture of the primordial vacuum. During the inflationary epoch, the universe was stretched from a tiny, homogeneous patch into a vast cosmos. That initial patch was in a state of exquisite order, a special low entropy condition. This was not a random state. It was a direct consequence of the vacuum's unique high-energy properties, a state of perfect uniformity that was then frozen into the fabric of the expanding universe by inflation's incredible pull. Think of a new deck of cards perfectly sorted by suit and value. This is a state of very low entropy. If you shuffle that deck, you increase its disorder, and it will never spontaneously return to its original, perfectly ordered sequence. The early universe was like that pristine deck. The quantum vacuum during inflation was the dealer that set the cards in perfect, improbable order. As the universe evolved from that moment, the only way to go was toward greater disorder, just as the only result of shuffling is a more mixed-up deck. This ever-increasing disorder is what we perceive as the forward march of time. The vacuum, therefore, is not just a spatial backdrop. Its specific initial condition imprinted a temporal direction onto the cosmos. The reason you remember the past is because it was a more ordered state, and the reason the future is unknown is because it holds a vast array of disordered possibilities. This creates a breathtaking link between the microscopic quantum realm and our most fundamental human experience. The fleeting dance of virtual particles and the grand, smooth geometry of the inflationary vacuum set the initial condition for a law that governs everything from the cooling of your coffee to the life cycle of stars. The arrow of time, the very flow of cause and effect, might be a direct inheritance from the unique, ordered nature of nothingness at the dawn of everything. If the void gave time its direction, what other fundamental aspects of our reality were whispered into existence by its hidden structure? The silent hum of the quantum vacuum is no longer just a theoretical whisper. It is a signal we are learning to measure with astonishing precision. In laboratories around the world, scientists are building devices to touch the texture of nothingness itself. The Casimir effect, once a stunning prediction, is now a standard tool in the nanotechnology toolkit. Researchers are not just confirming the effect exists, they are exploring its intricate details, measuring the force between objects of different shapes and materials with nanometer accuracy. These are not simple metal plates anymore, but complex nanostructures where the subtle push and pull of virtual particles can influence the operation of tiny machines. Each new measurement is a direct probe into the seething energy of empty space, testing the very predictions of quantum field theory at the most intimate scales. Beyond these delicate force measurements, other experiments aim to stir the vacuum into a more dramatic revelation. Imagine focusing the most powerful lasers ever conceived onto a single, empty point in space. These are not mere beams of light, they are instruments capable of warping the fabric of the void. The goal is to achieve such an immense concentration of energy that the vacuum itself begins to boil. This is the Schwinger effect, a process where the void, stressed beyond its limits, spontaneously breaks apart into real, detectable particles and antiparticles. It would be the ultimate act of creation from nothing, a laboratory-scale Genesis event that would confirm our deepest understanding of how fields and particles intertwine. While this has not yet been achieved in a definitive way, each new generation of laser technology brings us closer to crossing that threshold, to making the invisible architecture of reality visibly crackle with existence. Other frontiers use the strange rules of quantum mechanics to listen to the vacuum's faint noise. In supercooled laboratories, physicists employ superconducting circuits and quantum optics to attempt a direct detection of vacuum fluctuations. These circuits are so exquisitely sensitive that they can, in principle, pick up the faintest whispers of energy loans and repayments happening around them. It is like trying to hear the gentle hiss of a quiet radio station buried under static, requiring not just powerful technology, but brilliant new methods of quantum amplification and signal processing. The challenge is monumental, but the payoff would be revolutionary, providing the first direct audio of the universe's foundational static. These are not abstract thought games. They represent a fundamental shift in our relationship with the cosmos. We are moving from being passive observers of the sky to active experimenters with the void. Every precise measurement of the Casimir force, every pulse of an ultra-powerful laser, and every quiet listening session with a superconducting circuit is an attempt to interrogate the vacuum directly. We are asking it questions, and the answers we receive are slowly filling in the missing lines of the cosmic blueprint. If we can learn to read this hidden script in our labs, what profound secrets might it reveal about the birth and fate of the entire universe? This bizarre dance between the vacuum and its energy leads us to a principle so radical it challenges the very nature of dimensionality. The holographic principle suggests that our universe, in all its rich, three-dimensional glory, might be a magnificent illusion. The true blueprint of reality could be painted on a distant, two-dimensional surface. The origins of this mind-bending idea lie in the thermodynamics of black holes. Physicists discovered that the maximum amount of information, or entropy, a region of space can contain is not proportional to its volume, as you might expect, but to the area of its bounding surface. A black hole's information content is tied to the surface area of its event horizon, not the volume of the singularity within. This was a profound clue that the fundamental description of space might be lower dimensional. Think of a hologram on your credit card. It is a flat, two-dimensional piece of film, yet when you shine light through it, it projects a stunningly realistic three-dimensional image that you can look around. The holographic principle proposes that our entire cosmos operates on a similar, though far more fundamental, level. Every particle, every force, every event within the three-dimensional volume of our universe, including you and everything you see, might be encoded on a vast surrounding two-dimensional boundary. We are not just in the universe, we are a projection of information stored at its edges. This forces a complete re-evaluation of the vacuum. That seething quantum foam, that vibrant superfluid of potential, may not be the foundation itself. It could be the projected image, the result of an unimaginably complex data processing happening on a cosmic hard drive we cannot see. The vacuum's properties, from its energy to its fluctuations, would be the emergent output of this holographic computation. This transforms our understanding of the cosmic blueprint. It is no longer a spatial architecture, a set of instructions for building in three dimensions. The foundation of everything is purely informational. The most basic ingredient of reality is not a field or a particle, but a bit of data. The solidity of the world, the feeling of depth and space, is a magnificent translation of a simpler, lower-dimensional code. If the universe is a hologram, then the very fabric of our reality is a kind of cosmic narrative, a story being written and projected from the edges of existence. Our own cosmic vacuum might be living on borrowed time. The seemingly stable void that birthed our universe, complete with its laws of physics, could be a temporary illusion. This is the startling implication of vacuum metastability. According to quantum field theory, our vacuum might not be in the true, absolute lowest energy state. Instead, it could be in a false vacuum, a state of precarious equilibrium. Picture a deep, narrow valley representing the true vacuum, the most stable state possible. Our universe is not in that valley. It is perched on a high plateau, a local depression that feels stable for now, but rests at a much higher energy level than the true minimum far below. This situation is metastable, meaning it is stable for an incredibly long time, but not forever. It is a cosmic accident waiting to happen. Given enough time, a random quantum fluctuation could provide the necessary kick, a form of quantum tunneling that allows a tiny bubble of the true vacuum to nucleate somewhere in space. This would not be an explosion in space, but a rewriting of space itself. The moment this bubble forms, it would begin to expand in all directions at the speed of light. Its boundary would be a wall of fundamental change, a wave of transformation that erases the very laws of physics as we know them. Inside this expanding sphere, the properties of the quantum fields would be different. The Higgs field could take on a new value. The constants that govern the strength of forces or the masses of particles could be completely altered. The universe inside the bubble would be unrecognizable and likely incapable of supporting any structure or life as we understand it. This is not science fiction, but a serious, albeit alarming, prediction that emerges directly from our most advanced equations. The fact that our universe has lasted for over 13 billion years suggests this event is incredibly improbable on human timescales. But on a cosmic timeline, it remains a possibility, a sword of Damocles hanging over all of existence. This reveals a terrifying fragility in our cosmic blueprint. The architecture of our reality, for all its intricate beauty, might be fundamentally unstable, a temporary configuration in a vast landscape of possible universes. This leads to an even more profound question. If our vacuum is just one possibility, what other realities are waiting in the shadows? The vacuum surrounding a black hole is a place where reality is torn in two. At the boundary of the event horizon, the fabric of spacetime is stretched to an infinite degree, and the quantum vacuum responds in a way that reveals its ultimate power. This is the stage for Hawking radiation, a process where the void itself becomes a cosmic alchemist, transforming the immense gravity of the black hole into a stream of real particles. It begins with a virtual particle pair flickering into existence just outside the point of no return. These are not particles in the classical sense, but fleeting excitations in the quantum fields, born from the vacuum's inherent uncertainty. Normally, they would annihilate each other in an instant, returning their borrowed energy. But here, at the precipice, the black hole's ferocious gravity intervenes. It can tear the pair apart, pulling one particle across the horizon into the black hole's depths, while the other escapes into space, forever free. The escaped particle becomes real, carrying away energy. To conserve energy, the black hole itself must pay the cost. The particle that fell in effectively has negative energy from the perspective of the outside universe, and it reduces the black hole's total mass. Over astronomical eons, this slow, steady trickle of escaping particles causes the black hole to evaporate. The vacuum is not a passive witness to this drama. It is the active engine, its quantum fluctuations providing the raw material, and the warped geometry of spacetime providing the mechanism. This is a direct conversion of pure gravitational energy into matter, a transaction mediated entirely by the properties of nothingness. This interplay between the vacuum and a black hole's gravity is more than a theoretical curiosity. It is a crucial testing ground for the long-sought theory of quantum gravity. Hawking radiation forces the two great pillars of physics, general relativity and quantum mechanics, to confront each other. One describes the smooth, curved spacetime of the black hole, while the other describes the probabilistic, flickering particles at its edge. Their meeting point is the event horizon, and the result is a paradox that challenges our very understanding of information. If a black hole evaporates, what happens to all the information about the matter that fell into it? Does it simply vanish, violating a fundamental quantum law? Or is it somehow encoded in the Hawking radiation, a faint whisper of a lost star's identity hidden in the thermal glow? The resolution to this information paradox remains one of the most heated debates in theoretical physics. It suggests that the architecture of nothingness, when pushed to its absolute limit, holds the keys to a deeper, more unified law of the cosmos. This vibrant, active void forces us to confront a question that has haunted philosophers for millennia. Why is there something rather than nothing? For centuries, this inquiry seemed straightforward. Nothing was the absolute absence of all things, a sterile void, a blank canvas waiting for a painter. But our journey reveals a shocking truth: the canvas itself is not blank. It is a complex, dynamic entity, humming with energy and governed by its own intricate laws. The question is no longer why there is something instead of nothing. It is why this particular, finely tuned something emerged from a nothingness that was already so full of potential. The distinction between being and non-being begins to blur into irrelevance. We traditionally define existence as the presence of observable properties, of things that can be measured and interacted with, yet the quantum vacuum possesses properties. It has a measurable energy density, it exerts pressure, and it has a specific structure that dictates the behavior of everything within it. If something has properties and structure, can we truly call it nothing? Or have we simply discovered a more fundamental layer of something, a something so subtle and pervasive that we once mistook it for absence? This moves our discussion from the solid ground of physics into the more nebulous realm of metaphysics. We are probing the very definitions we use to carve up reality. The ancient Greek concept of the void, as proposed by Democritus, was a passive emptiness, a stage for atoms. Quantum vacuum is the stage, the actors, and the script, all woven together into a single, inseparable whole. This challenges our most basic intuition about what is real. Is a virtual particle that exists for a septillionth of a second less real than an electron, when the effects of those fleeting ghosts are permanently etched into the energy levels of atoms and the eventual evaporation of black holes? The reality we experience may just be the most stable and persistent excitation on a deeper, more chaotic plane of existence. Our entire universe, with its galaxies and conscious life, could be a kind of stable pattern, a standing wave in this fundamental field of potential. This perspective does not invalidate science, it enriches it. It suggests that the laws of physics are not arbitrary rules imposed upon an empty container. They are the emergent properties of this active nothingness, the natural dynamics of the vacuum itself, the force of gravity, the speed of light, the mass of an electron. These may not be fundamental constants handed down from on high. They could be the inevitable outcomes of the specific way our cosmic vacuum is structured. This realization forces a profound re-evaluation of our place in the cosmos. We are not isolated beings living on a rock in a sterile emptiness. We are intricate patterns woven from the same vibrant tapestry as the space between the stars. The void is not an other, it is us. Every atom in your body is a localized excitation in a field that is everywhere, and the space between those atoms is teeming with the same creative ferment that birthed the cosmos. You are not in the universe, you are of the universe, and so is the nothingness that gives it form. This hidden architecture of nothingness is already stepping out of theory and into our laboratories. The subtle push of the Casimir effect, once a stunning confirmation of quantum weirdness, is now being harnessed. In the world of nanotechnology, where machines are built atom by atom, this force is no longer a curiosity, it is a fundamental factor. Engineers designing micro-electromechanical systems, or MEMS, tiny devices with moving parts smaller than a dust mite, must account for the vacuum's influence. At these scales, the relentless pressure from virtual particles can cause components to stick together, a phenomenon called stiction, or it can be intentionally used to create ultra-sensitive switches and actuators. We are learning to build with the vacuum, using its invisible push and pull to guide the operation of machines so small they operate in the realm where nothingness has a tangible force. This is not future speculation. It is happening now in clean rooms and research facilities, turning the quantum blueprint into a practical engineering principle. But what about grander manipulations of this cosmic substrate? The equations of general relativity allow for a breathtaking possibility, the warp drive. Popularized by science fiction, the concept has a serious theoretical foundation in physics. The Alcubierre metric, proposed by physicist Miguel Alcubierre, is not about building a faster engine. It is a proposed method of engineering spacetime itself. The idea is to create a bubble of flat space around a ship, while compressing the spacetime in front of it and expanding the spacetime behind it. In this scenario, the ship itself does not move through space. It is the space around it that moves, carrying the ship along like a surfboard on a wave. This could, in theory, allow for apparent faster-than-light travel without violating relativity, because locally, inside the bubble, the ship is stationary. The fuel for this incredible journey would not be conventional matter, but a specific configuration of the vacuum's energy density. To form the warp bubble, you would need a form of negative energy, or exotic matter, something that the quantum vacuum with its negative pressure might theoretically provide. While this remains highly speculative and faces immense practical challenges, it demonstrates a profound shift in thinking. It shows that the vacuum is not just a backdrop for physics, but a potential material for technology. The void is a construction site. These applications, from the nanoscale to the interstellar, point toward a single, staggering conclusion. Humanity's ultimate mastery over the cosmos may not come from building bigger rockets, but from learning to read and manipulate the hidden lines of the cosmic blueprint. The vacuum is the final frontier of engineering. Its quantum whispers, if we can learn to amplify and direct them, could power civilizations, reshape worlds, and carry us to the stars. We are just beginning to understand the tools, but the workshop is all around us, in every cubic centimeter of apparent emptiness. The silent hum of nothingness may one day become the engine of our destiny. If the vacuum is the ultimate foundation of reality, could it also be the source of our own inner world? This question leads us to the most speculative frontier of all, a potential bridge between the architecture of nothingness and the mystery of consciousness itself. Some prominent theorists, including the Nobel laureate Roger Penrose and anesthesiologist Stuart Hameroff, have proposed a breathtaking hypothesis. They suggest that the brain's neurons are not the whole story. Deep inside your brain cells are structures called microtubules, tiny protein scaffolds that help maintain the cell's shape. Their theory, called orchestrated objective reduction, posits that these microtubules are more than just structural supports. They could be quantum computers protected within the brain, where gravitational influences from the fabric of spacetime itself can cause wave functions to collapse. This is where the vacuum enters the picture. Remember, spacetime geometry is not a fixed stage. It is the dynamic, fluctuating quantum vacuum. If consciousness arises from these delicate quantum processes, then the foundational level of reality, that seething sea of potential, could be directly participating in the emergence of mind. Your thoughts, your awareness, might not be generated by a classical computer made of meat, but by an intricate dance between biology and the fundamental vibrations of the cosmos. This idea is, without question, highly controversial and sits far outside the scientific mainstream. The warm, wet, and noisy environment of the brain seems profoundly hostile to the fragile coherence required for quantum effects. Most neuroscientists see consciousness as an emergent property of complex neural computation, not quantum gravity, yet this fringe theory serves a profound purpose. It stretches our imagination to its absolute limits, forcing us to consider how deep the implications of the vacuum's blueprint might truly run. If even a sliver of this connection were valid, it would mean that subjective experience, the feeling of being, is not separate from the universe. It is a reading of the cosmic code, a manifestation of the vacuum's hidden activity. The silent hum of empty space and the inner voice of your consciousness could be different expressions of the same fundamental reality. This speculative link pushes our inquiry to its final, most intimate boundary, suggesting that in understanding the void, we might ultimately be deciphering the origins of ourselves. Our universe may not have a single, definitive beginning. The Big Bang is the dominant story of our cosmic origin, but it is not the only tale the equations of physics can tell. Competing visions of reality have emerged, each giving the quantum vacuum an even more profound and eternal role. One of the most elegant challenges was the steady-state model. Proposed in the mid-20th century, it rejected the idea of a primordial explosion. Instead, it argued for a universe that had no beginning and will have no end, eternally maintaining the same average density. But how could this be if the universe is expanding and galaxies are flying apart? The theory introduced a hypothetical creation field, or C field. This field, woven into the fabric of the vacuum, would continuously and imperceptibly generate new matter from nothing, just enough to fill the gaps as the universe expanded. In this view, the vacuum was not a passive witness but an active, eternal fountain of creation, constantly birthing new hydrogen atoms to keep the cosmos looking forever young. This model was eventually dethroned by the discovery of the cosmic microwave background radiation, the definitive afterglow of a hot, dense beginning. Yet its philosophical challenge remains, suggesting that the vacuum could possess an inherent, endless creative power. An even more dramatic alternative is the cyclic universe. In the ekpyrotic model, our cosmos exists on a three-dimensional membrane, or brain, floating in a higher dimensional space. The Big Bang was not a moment of creation from nothing, but the result of a collision between our brain and a neighboring one. The immense energy of this collision heated our universe to a phenomenal temperature, mimicking a Big Bang, and then set it on its course of expansion. But the story does not end there. The theory proposes that these brains are drawn together over trillions of years, destined to collide again and again in an endless cycle of cosmic death and rebirth. Each collision is a new bang, each expansion a new chapter in an infinite saga. In this breathtaking vision, the vacuum of the higher dimensional bulk is the true constant. Our entire universe, with all its galaxies and laws, is merely a temporary event, a repeating pattern within an eternal, multidimensional void. These models fundamentally redefine the Big Bang. It is no longer the ultimate beginning, the moment something emerged from nothing. Instead, it becomes a phase transition, a dramatic but local shift in the state of a pre-existing eternal vacuum. The void is not a consequence of the universe is a consequence of the void. This perspective inverts our entire understanding of reality. We are not living in the aftermath of a singular creation event. We are inhabitants of one bubble in an endless, perhaps infinite, cosmic foam, where the vacuum is the only true permanence. If our cosmos is just one episode in an infinite cycle, what does that say about the uniqueness of our existence and the ultimate fate of everything we know? This cosmic hologram requires a processor to bring it to life. The universe might not just contain information, it might be actively computing it. If the holographic principle paints reality as a projected image, then the quantum vacuum at the Planck scale is the unimaginable hardware running the code. Each discrete unit of that foaming spacetime, each tiny pixel of reality, could be thought of as holding a single bit of quantum information, a 1 or a 0 in the most fundamental sense. The entire cosmos would then be a vast dynamic network, a cosmic computer where these bits interact, flip, and entangle according to a set of fundamental rules. In this view, the laws of physics are not merely descriptive equations we discovered. They are the operating system, the elegant algorithms that govern the flow of information across the network. Gravity, electromagnetism, the nuclear forces, these would be the emergent software, the programs that arise from the relentless underlying computation. What we perceive as a particle collision or a star's life cycle is simply the visible output of this constant, invisible processing. The vacuum is transformed from a stage or a superfluid into an active cosmic CPU. The Big Bang was not an explosion in space, but the initial boot-up sequence. The expansion of the universe is the continuous execution of the code, generating more space-time and thus more processing power as it runs. This computational perspective offers a powerful new metaphor for the cosmic blueprint. We are no longer just reading a static architectural plan. We are witnessing a live simulation, a cosmic narrative being generated in real time by the silent, ceaseless hum of the vacuum itself. The question then becomes who or what wrote the program, and what is the ultimate purpose of its breathtaking output? Symmetry is the silent architect of the cosmos, a hidden order written into the laws of physics that dictates the very structure of the void. This is not the symmetry of a beautiful face or a snowflake, but a deeper, more fundamental mathematical balance in the equations that describe reality. In its most perfect, pristine form, this symmetry would produce a universe of pure potential, where all forces are unified and particles are weightless, zipping through a featureless void. Our universe, however, is rich with diversity and structure because this perfect symmetry did not last. It broke. This process, known as spontaneous symmetry breaking, is what carved the specific properties of our vacuum from a sea of infinite possibilities. Imagine a perfectly sharp pencil balanced on its point. That pencil is in a state of perfect symmetry, identical from every horizontal direction, but it is also unstable. The slightest disturbance, a random quantum whisper, will cause it to tip and fall, landing in one specific direction. The perfect symmetry is broken, and a specific, preferred orientation is chosen. The Higgs field underwent a similar cosmic tipping point. In the searing heat of the early universe, it existed in a state of perfect symmetry, a high-energy plateau where it gave mass to nothing. As the cosmos cooled, this symmetric state became unstable. The Higgs field settled into a specific, non-zero value everywhere, like that pencil choosing a direction to fall. This breaking of symmetry is what gave mass to the fundamental particles, sculpting the specific vacuum state that allows for atoms, planets, and us. Our reality is not a product of perfect order, but of a specific, fruitful brokenness. This principle extends far beyond the Higgs. The very forces of nature we experience as separate, gravity and electromagnetism, and the nuclear forces, may have been unified in a single, symmetric force at the universe's birth. As the vacuum cooled and evolved, symmetries broke in a cascade, freezing out the distinct forces and particles we recognize today. This leads to a staggering implication about the multiverse. If a landscape of possible vacuum states exists, each one corresponds to a different pattern of broken symmetry. In one bubble universe, a different symmetry might have broken, leading to a vacuum where electromagnetism is 1,000 times stronger. or where quarks have no mass, creating a cosmos utterly alien to our own. The specific architecture of our nothing, with its precise constants and laws, is not a random accident. It is a single, elegant solution to the mathematical question of which symmetries broke and how. Beneath the apparent chaos of quantum foam and virtual particles lies a deep and profound beauty, a cosmos shaped by the breaking of its own perfect order. The silent hum of the vacuum is about to meet its match in a new generation of cosmic listeners. Our quest to decode the blueprint of nothingness is accelerating, driven by technological marvels that will push our vision to the absolute limit. Orbiting 1,000,000 miles from Earth, the James Webb Space Telescope is not just another observatory. It is a time machine calibrated to weigh the void itself. By peering back at the very first galaxies to form after the Big Bang, it will trace the history of cosmic expansion with unprecedented precision. Each measurement of a distant supernova, each map of the large-scale structure of the early universe, is a data point in the grand equation of dark energy. Is the vacuum energy truly constant, or has its repulsive push changed over billions of years? The answers from Webb will either solidify our current models or force a revolutionary rewrite of cosmic history. Back on the ground, the search turns inward to the realm of the impossibly small. Plans are already underway for the next generation of particle colliders, machines of staggering scale and power designed to tear aside the veil of our current vacuum. These colossal rings or linear accelerators would smash particles together with energies far beyond what the Large Hadron Collider can achieve. The goal is to recreate, for a fleeting instant, the conditions of the primordial high-energy vacuum, the state that existed before symmetry broke and gave mass to the universe. In the fiery debris of these collisions, physicists hope to find the fingerprints of new symmetries, or even entirely new particles, that could explain the vacuum's perplexing fine-tuning. They are probing for the hidden gears and levers that set the properties of our cosmic foundation. Perhaps the most audacious experiments aim to feel the texture of space-time itself. If the Planck scale is a seething quantum foam, its effects are unimaginably tiny, but not necessarily undetectable. Innovative laboratory setups are using ultra-precise lasers, supercooled mirrors, and even beams of entangled particles to hunt for the faintest whispers of this granularity. The idea is to watch light or particles travel over long distances and look for minuscule fluctuations in their arrival time or phase, a potential sign that they are buffeted by the foamy structure of space-time on their journey. It is like trying to detect the individual molecules in a pane of glass by studying how a light beam shimmers as it passes through. Success would provide the first direct evidence that the smooth continuum of space-time is an illusion, revealing the pixelated heart of reality. This global symphony of discovery, from deep space telescopes to underground colliders and tabletop quantum experiments, represents a unified assault on the greatest mystery in physics. We are no longer just contemplating the vacuum. We are building tools to interrogate it, to stress it, and to listen to its quietest vibrations. The hidden architecture of nothingness has remained elusive for centuries, but the walls of its secret chamber are finally beginning to tremble. What profound secrets will it be forced to surrender when we learn to ask the right questions with instruments of such exquisite sensitivity? This final unification of forces remains the ultimate goal of physics, a single mathematical framework that describes the cosmos in its most fundamental state. Imagine tracing the history of the universe backwards in time towards the searing heat of the Big Bang. As we rewind, the distinctions we see today begin to blur. The electromagnetic force and the weak nuclear force, which appear so separate in our cool modern universe, merge into a single electroweak force, push back even further, and theory suggests this unified force would combine with the strong nuclear force, leaving only gravity as the stubborn outlier. In that primordial instant, all of reality was governed by a single, supremely symmetric law. The vacuum of that era was not the complex, broken state we inhabit now. It was a perfect, featureless unity, a state of pure potential where every force was one and the same. Our current reality, with its 4 distinct forces and a zoo of particles, is the frozen, fragmented remnant of that initial perfection. This fragmentation occurred through a cascade of cosmic phase transitions, like water freezing into ice. As the universe expanded and cooled, the symmetric, high-energy vacuum became unstable. It underwent a series of symmetry breaks, each one locking in a new set of properties and carving the separate forces and particles from the unified whole. The Higgs field acquiring its value was one of the last and most crucial of these breaks, giving mass to the universe and finalizing the forces we know. The quest for a theory of everything is at its heart an attempt to describe that original, perfectly symmetric vacuum. String theory, for instance, proposes that the fundamental entities are not point-like particles, but incredibly tiny, vibrating loops of energy. The different vibrational patterns of these strings manifest as the different particles and forces. In this view, an electron is not a dot, it is a specific note being played on a cosmic string. The vacuum is the silent instrument itself, waiting to be strummed into existence. Loop quantum gravity takes a different approach, suggesting space-time itself is woven from a network of discrete, finite loops. Here, the vacuum is this fundamental spin network in its ground state, and particles are excitations of its fabric. Despite their different paths, both theories, and others like them, aim for the same destination, a single equation from which the entire cosmos unfurls. Achieving this would be the final chapter in our understanding of the cosmic blueprint. It would reveal that the seething quantum foam, the Higgs field, and the force of gravity are all different faces of a single, breathtakingly simple entity, the unified vacuum. To know this ultimate architecture would be to read the mind of the universe, to understand why there is something rather than nothing, and to see that the magnificent diversity of our world emerges from a silent, foundational unity. We began this journey picturing the void as a silent, empty stage, a passive backdrop for the cosmic drama, but we have discovered something far more astonishing. The vacuum is the lead actor, the playwright, and the theater itself, a dynamic quantum field teeming with potential. It is the source of mass, sculpting the very substance of our world through the Higgs field. It is the engine of dark energy, accelerating the expansion of the cosmos with its own intrinsic repulsive push. It forged the entire universe in a flash of inflationary stretching, transforming quantum whispers into the gravitational seeds for all structure. And in our most radical theories, it may even be a holographic information processor, projecting our rich 3-dimensional reality from a 2-dimensional boundary. This is not a minor adjustment to our worldview. It is a complete transformation of our place in the cosmos. We are not merely inhabitants of space, living on isolated islands of matter. We are vibrant expressions of its deepest, most fundamental structure. Every atom in your body is a localized excitation in this universal field, and the space between your atoms hums with the same creative energy that birthed the galaxies. The search to understand nothing has revealed the richest something imaginable, a hidden architecture that is both the foundation of reality and the source of our own existence. Let this new perspective forever change how you look at the night sky, seeing not emptiness but a vibrant, creative canvas. What does this profound connection between the void and existence inspire in you? Share your thoughts and questions in the comments below, and subscribe to continue exploring the universe's greatest mysteries with us.